Thank you.
Stage is yours.
Yep. Thank you very much. This is my first talk in person, I think, after 3 years. So I'm very happy to be here. Why am I here? So think Baja instead of formula. That's how I think about it, right? So you want to race really fast, but you want to race in off-road conditions. I'm also the faculty advisor for the Formula Baja and the Formula Electric teams at Texas A&M, right? I would say I know how vehicles fail. We have at A&M, we have a long history of winning the Formula SAE competition. I think we've won it the most amount of times. We did not win this year, and I will not tell you who won it. So you can look it up. I wanted to start off by kind of giving you an overview of what are the hard problems, right, when you're trying to do this in off-road environments. And then kind of give you an overview of what we've been working on at my group for the last couple of years and high-speed off-road autonomy, and then kind of leave you with a couple of thoughts on what's next and what we need to solve, right? So let's see, hopefully all of these play. Probably not. Oh, okay. Mm-hmm. So I have to use this?
Yeah.
Okay. Yeah. So the first video that you see, that's autonomously traversing probably at about 2-3 meters per second. It's trying to cross, go to the other end of that gorge, if you want to call it, and it gets stuck there, right? So obviously, that was the most flattest part through which it could go, but as it turns out, that's quicksand, right? And even though that's a 4-wheel vehicle, it got stuck in quicksand, right? So this is again trying to climb that hill, right? Again, autonomously. Oops, and then we took over. So you could even, right? So it was going to flip over, right? Again, so dynamics are very, very important. Of course, you can high center, right? Again, autonomously, if you don't know that your sensors can't detect what's in front of you properly, either because you do not have the proper field of view or you're not computing it fast enough, then you can high center, right? So, right, so think about hard problems and off-road domains, right? How do we detect quicksand, right? So how do we know what the load-bearing surface is? Where should we be driving, right? How do we know, how can we think about stability of the vehicle, right? Particularly when you're not going in 2 or 2.5D terrain and you're trying to go really climb up hills, things like that, right? And then, of course, how do you know that you have all kinds of negative obstacles? How can you detect them, and how can you try solving them, right? So this is kind of like the slide that kind of describes what the hard problems are right now, right? So lack of data sets. Really, most of the perception, planning, and control algorithms that are built right now are really built for on-road autonomous vehicles, right? And so when you start thinking about off-road autonomy, there are not that many data sets. And I'll come to this later, but most of your semantic perception, most of your semantic perception algorithms fail when you think about off-road autonomous situations, right? It's very hard to detect things like bushes, trees, plants, things like that, right? And also furthermore, to kind of think about things like, I should go through bushes. So soft versus hard obstacles. I should not hit a tree, but it's okay to go through bushes, right? So those are hard things. Where to go, right? So if you think about on-road autonomy, you have a road, you know where to go, right? You have different problems to solve, but at least that's a problem that you very clearly know what to do, right? In off-road situations, load-bearing surfaces, where exactly should you go? What's beneath your grass? Where is it mud? Is it soft soil? What kind of soil is there becomes really, really important, right? And that becomes much more important when you're trying to do this at higher speeds, right? So when I mean higher speeds, I want to quantify it. We're talking it about between 5 to 10 meters per second. So in terms of miles per hour, you're kind of looking at between 10 to 22 miles per hour, right? And how fast to go, right? Dynamics, suspension, terrain, wheel terrain interaction, these kind of things become really, really important, right? So I'm kind of going to give you an overview of the things that we've been working on. So the first thing that I said is, of course, data sets. So one of the first things that we did is we went and collected multimodal data in high off-road environments, right? And then we open source this data. But not only, so it consists of both LiDAR, imagery data, along with GPS, IMU data, annotated both in imagery and LiDAR, right? And the reason, if you think about it, is I'll show you the data and then I'll kind of give you some benchmarks on that. So this is what the data looks like. So what you see, the bottom right is segmented data. The top right is the actual image. And the center that you see is segmented LiDAR data, right? So synchronized multimodal data that you can use for developing your semantic segmentation, your off-road algorithms, right? And the reason why we did this is we kind of wanted to ask the question, are the current state of the art semantic segmentation algorithms good enough, right, on an off-road data set? As it turns out, that's not the case, right? So most of these algorithms, if you look at it, what you have is a pretty bad imbalance between what you see. So things like, if you wanted to look at dirt, most of the times you're looking at sky, things like that. So you need a lot of the times you have a pretty high imbalance between the kind of data that you can get and the things that are most important for you, right? So things like grass, tree, bushes, right? They're very little, they're very small of the data set. Furthermore, when we ran this on something like say some of the state of the art, both LiDAR semantic segmentation as well as image semantic segmentation, you can see that you only get about 50% mean IOU, right? While if you ran them on something like Cityscape, which is a standard data set that is used for evaluating semantic segmentation algorithms, you have about 80% mean IOU, right? What that means is that we need more data so that you can generalize this algorithm so that not only do they work in on-road scenarios, but they are also relevant to off-road scenarios, right? And so we've done some work. Along with that, another one that we've looked into is what about the state of the art that's there in visual inertial odometry, right? So most of the times when you have these data sets, when you're trying to do this in off-road situations, you're looking at GPS denied environments. Right. Again, we have another data set that we have specifically created for off-road environments. And we've evaluated, again, various kinds of visual inertial odometry algorithms to see how well they are, right? Again, as it turns out, this is slightly better than the semantic perception algorithms in the sense that they work most of the time. But of course, when you have fairly high pitch variations and roll variations, these algorithms fail, right? Which is kind of to be expected, right? So once you have this data set, the kind of questions that we are interested in is where do you want to go, right? So really, so if you think about a semantic segmentation data set, you kind of segment things like grass, leaves, bushes, trees, things like that, right? But if you're driving an off-road and if you want to drive really, really fast in off-road environments, the question that you're asking is, can I think about traversability? What is a traversable surface? What is a non-traversable surface? And can I do that, right? So here's one variant of what we have come up with. If I can get my mouse. Right, so here we have a fairly simple algorithm that looks at traversable versus non-traversable surfaces, right? So it's basically looking at the imagery data, and it's very quickly determining what's a traversable surface and what's a non-traversable surface, so that you can use this to kind of make decisions about where you want to drive versus where you don't want to drive, right? And if the papers are there, so you could look at these things afterwards. But once you've determined where you want to drive, right, you want to drive quickly. and you want to be able to determine hard and soft obstacles, right? And you want to be able to do this in unstructured off-road terrains where you do not have GPS, right? So our way of doing this is really looking at it from, um, looking at LiDAR data, looking at imagery data, trying to determine what a hard obstacle is and what a soft obstacle is, and then creating a local voxel map on the GPU so that you could do this really, really fast. And then using a actuator-based planning so that you plan an actuator space so that you are able to drive fast, right? And I'll show you videos of it. I'm happy to discuss the actual technical details of it later if anybody is interested in it, right? So this is one of our first attempts at doing this, right? So what you see here on the top left, right, is the vehicle driving. So what it's given is a waypoint about in GPS coordinates about 200 meters, right? But it needs to determine still how to get there without using GPS. So really all it's using is LiDAR data, imagery data, and inertial data, right? So it creates a local map, then it creates multiple maps, which you see at the bottom. So things such as a height map, an obstacle map, and then it avoids these obstacles and is able to then go around these obstacles and is able to navigate, right? So this is at about 3.5, 4 meters per second. So not fast enough, but fast enough where people have to run so that you're always afraid of what happens with this, right? So the next one, of course, is shows the same thing, but here you're looking at it from, can it avoid hard obstacles while being able to navigate through soft obstacles, right? So this is a made up scenario where you have these hard obstacles that it needs to avoid, but it's okay to go through those bushes over there so that now it can go through these soft obstacles, so grass, but not avoid these hard obstacles, right? And now you get to the point, okay, so now I've done this. Can I do this at a high enough speed? So here it needs to kind of avoid that big, tall hill and then go to that point, that given GPS waypoint, right? At about speeds of 4.5 meters per second. Okay, so here, what you're doing is to get it to the point of 4.5 meters per second. What we did is we took the standard voxel mapping and then we basically transported it from using it on the CPU to doing everything in the GPU, right? So this is again a paper that we have where we create a voxel map and cost maps from that. So things like a height map, roughness map, a negative obstacle map, things like that, but everything in the GPU so that now you can start looking at how do you go faster, right? So here, let me see if I can. Yeah, right. So this is at about 4 meters per second. So what you have on the right are opacity. At the bottom is a height map. And the bottom right one is you have hard and soft obstacles, right? Again, the vehicle is given a waypoint every 200, 250 meters. So it really only knows that it needs to get to that 250 meters. But in between that, it's free to kind of roam around and figure out the path through which it's going. So this kind of shows you how it's able to do this, right? At 4 meters per second. Okay. Running it. And so the next question, of course, is can you do this at a long enough distance? And I won't let you, oops. So I'll just show you a couple of things, but here you have the same thing running. This is about a kilometer long area where you have the vehicle going through. There's a path, but there are, of course, trees, bushes, other kinds of things over there where it's avoiding that and it's passing through, right? So all this is great, but really you're still at 4 meters per second. So 4, 5 meters is still 10 miles per hour, right? So this is not really high-speed off-road navigation. what this is building up all the system tools so that you can get to the next step, which is you really want to go at 8, 9, 10 meters per second, right? So one of the things then we realized is to get there. So we built up the tools and GPU for voxel-based mapping. We have tools that we have built up for control, but for planning, which uses an actuator-based planning, but we really then wanted to build up the tools for being able to do control using reinforcement learning so that you can do this. So this is 4, I think it should be 8. Oops. Right. So that is now running at 8 meters per second, right? And so this is really where I said, think Baja. Right. So it's still not fast enough. We'd like to go. So the Warthog that I was showing, the vehicle that I was showing, that is really limited to about 4.5 meters per second. You really can't go faster than that. But this is the Moose. This can really go up to, up to 8 meters per second. Nope. Okay, anyway, this can go up to 9, 10 meters per second. What you see in the right picture, the green is kind of the approximate trajectory. So based on waypoints that the moose should traverse, the red kind of shows what the trajectory the moose is taking, traversing this. So we have not got all the pieces in place so that we're able to do what I would state as high-speed off-road navigation. Of course, there are still a lot of problems that I think we need to solve. To be able to do this in a realistic, robust way, we definitely need diverse off-road data sets, right? Better data sets are always more diverse data sets. There is a lack of off-road data sets, particularly multimodal. So you have a lot of imagery data sets that are available, and there are data sets, but there are very, very few LiDAR data sets, and there are literally almost 0 radar data sets in off-road domains, right? So you need those to be able to solve this, right? The next big problem is how good should simulators be, right? So if you take the current simulators, they're very specific to on-road simulators. On-road autonomy solutions. When you're thinking off-road, you need to think about dual returns from LiDAR. You need to think about how light reflects from trees, things like that. So the current simulators are really, really lacking in simulating sensors, right? So you can, of course, ask the question whether you need better simulators or whether you need worse simulators, because you might not be able to actually simulate every environment that you have, right? So that's an interesting question to ask. But if you want to be able to test these, you definitely need better simulators where you can test this, right? A big challenge that I personally think one needs to solve, that we've been working on for a long time, is cross-calibration between sensors. You have a lot of sensors. Sometimes you have multiple IMUs, multiple LiDARs, multiple cameras, and multiple radars. You do not want to be sitting somewhere and figuring out, having a checkerboard. Anybody who's worked on field robotics hates checkerboards. I'm sure all of you share the same thing with me. So we do not want to be doing checkerboard calibration, right? Online calibration is something that I think we need before we can go to the next step in this, right? Robustness of our algorithms, right? So we can train our algorithms, whether they're reinforcement learning, whether they're deep learning, semantic perception algorithms for a particular area. Better data sets allow us to get it to much more diverse environments, and then lots more testing, right? This is where the fun part comes, which is you need to be able to test in different kinds of environments so that you're able to get these to the point where the goal really is to go at about 15 meters per second, right? So that's a typical Baja competition, right? If you can go at about 15 meters per second in off-road environments, then you are able to compete in a Baja tournament. So I'll leave it there. Thanks a lot.